If I have a hereditary weakness in breaking down branched chain amino acids, what cofactors do I need to consider for vitamins and minerals? And do I need to restrict my protein when losing weight?
This is a clip from a live Q&A session open to CMJ Masterpass members. In addition to this episode, you can access lots of other free samples from these sessions at the first link in the description.
We will now go to the last runner-up. And this question comes from Melanie, and her question in my summary is, if I have a hereditary weakness in breaking down branched chain amino acids, what cofactors do I need to consider? And do I need to restrict my protein when losing weight? Her full question is, what exactly does it mean that leucine is a ketogenic amino acid? If a person has a hereditary weakness for branched chain amino acid catabolism, would this impact the type of diet they might choose to lose weight? Should they limit protein if it will increase their need for nutrients like biotin? What are all the possible cofactors we should consider supplementing to support leucine catabolism? All right, so I'm going to answer this first by answering, what are the cofactors that you need to break down branched chain amino acids? All right, so all the branched chain amino acids are leucine, isoleucine, and valine. And they all have very similar metabolism. In one case, the enzyme is shared. And in most cases, the enzymes are analogous and require similar cofactors, but there are some differences. So if you look at these numbers, this chart comes from the branched chain organic acidemia aciduria chapter of the the newest edition of Inborn Metabolic Diseases Diagnosis and Treatment by Saudubre and other editors. So, and then I added the cofactors. So this was my research that I layered on top of this diagram. So leucine, isoleucine, and valine all pass through the same first enzyme in common. And this is the branched chain alpha ketoacid dehydrogenase complex. And its cofactors are B1, which is thiamine, B2, which is riboflavin, B3, which is niacin, B5, which is pantothenic acid, lipoic acid, calcium, and magnesium. So this first step is shared across all three branched chain amino acids. And when we refer to pantothenic acid, we're referring to it here as coenzyme A. And so what you see is 2-oxo-isocaproic acid, after this step, is converted to isovalerol-CoA. That's because B5, or pantothenic acid in the form of CoA, captured the metabolite as a CoA ester. And then you see the CoA stays there. So in a way, B5 is a cofactor for the rest of this, but B5 isn't used again. It's just staying there in the form of CoA that later gets cleaved after this step. Now, after you get to past the first step, you no longer have the first enzyme shared in common. You now have analogous enzymes. So in the case of leucine, you have the enzyme isovalerol-CoA dehydrogenase, which is dependent on B2, which is riboflavin. In the case of isoleucine, you have enzyme number 6, that's short branched chain acyl-CoA dehydrogenase. And this is also dependent on riboflavin, or B2, because it's the analogous enzyme as the dehydrogenase over in leucine. If we look at valine, we have a different enzyme, number 9, which is isobutyryl-CoA dehydrogenase. And this is a riboflavin-dependent enzyme. So even though these are 3 dependent enzymes catalyzing the second step, they're all dependent equally on riboflavin because they're all analogous enzymes doing analogous reactions. After you get to this part, it gets a little bit different. So in the case of leucine, you have a biotin-dependent step that is not present in the other 2 branched chain amino acids. You have enzyme number 3, which is beta-methylcrotenyl-CoA carboxylase. If you read my recent biotin article, you saw the cases of genetic beta-methylcrotenyl-CoA carboxylase deficiency. as a sometimes and perhaps always biotin responsive disorder. And that enzyme requires biotin as well as ATP. Biotin dependent reactions are anabolic. They are ATP dependent. Everything that depends on ATP depends on magnesium, because most ATP functions as a magnesium chelate. Although there's a small amount of ATP that also has that is also chelated with other divalent cationic minerals, which means minerals with +2 charges. But magnesium is overwhelmingly the dominant one. Now, in the third step with isoleucine, we actually have a reversible non-enzymatic reaction between the product of the second reaction, Tiglyl-CoA, and 2-methyl-3-hydroxybutyl-CoA, before we get to the next enzyme. Going back to these steps, the third and fourth step in leucine metabolism, we have the biotin-dependent step, and then we have the fourth step catalyzed by 3-methyl-glutathione-CoA hydratase. The several water dependent steps with hydrolases with hydrolases and hydratases in all of this are the steps that have no cofactors. And so we have this water dependent step in the fourth step in leucine catabolism. In isoleucine, the fourth step is a dehydrogenase. That's 2-methyl-3-hydroxybutyl-CoA dehydrogenase. The dehydrogenases tend to be niacin dependent, as is the case here. And then in valine, we have 1, 2, 3. The fourth step is 3-hydroxyisobutyl-CoA hydrolase. That's the water dependent step with no cofactors. And then the fifth step is enzyme number 12, which is 3-hydroxyisobutyric acid dehydrogenase. Dehydrogenases are generally niacin dependent, as is the case here. And so we have this analogous niacin dependent step in isoleucine and valine metabolism that is not present in leucine metabolism. And then at the end, the fifth step in leucine catabolism is catalyzed by 3-hydroxy-3-methylglutarol-CoA lyase, which is dependent on magnesium or manganese that can substitute for each other. And then in the case of isoleucine, we have the eighth enzyme, which is 2-methyl-acetoacetyl-CoA thiolase, which is dependent on potassium and chloride. This enzyme is the same enzyme, the same thiolase enzyme that is used in ketone utilization. And so some people have a disorder in this enzyme. It's thiolase deficiency, and their disorder will become activated on a ketogenic diet because they're using the limited capacity of that enzyme for the ketones, and they don't have it available for the last step of isoleucine metabolism. And potassium and chloride, theoretically have therapeutic value there because this enzyme is dependent on those two minerals. Over in valine, we have the 13th enzyme, which is methylmalonic semialdehyde dehydrogenase, which is dependent on pantothenate and niacin. And in both of these cases, for isoleucine and valine, but not for leucine, we have the production of propionyl-CoA. And propionyl-CoA carboxylase is needed to clear that, which is dependent on biotin and magnesium and ATP. Propionyl-CoA carboxylase is another biotin-dependent isolated carboxylase deficiency discussed in the article that I had put out 2 days ago. And then we have that results in the production of methylmalonyl-CoA, which we need methylmalonyl-CoA mutase to turn into succinyl-CoA with the help of vitamin B12 and magnesium. And so note that many people are using methylmalonic acid rising as an indicator of B12 deficiency, apart from the fact that more rarely this could be a genetic methylmalonic acidemia, although it's probably not that rare to have it being influenced by carrier status for genetic methylmalonic acidemia, which no one ever knows they have. If you have a biotin deficiency, you're going to have low methylmalonic acid. And so, just briefly, there's someone on my Facebook who was saying that her daughter was in and out of the ER with alternating acidosis and alkalosis. And anyone who ever measured her methylmalonic acid thought it was great because it was low, and that indicated that her B12 was deficient, and actually indicated that she needed biotin. Biotin resolved all her symptoms, although I suspect that she had a genetic methylmalonic acidemia that was biotin responsive, and high dose biotin resolved all the symptoms because it activated the enzyme. And so, to sum this up, what are the nutrients you need in total to metabolize branched chain amino acids? Well, they're thiamine, riboflavin, niacin, pantothenic acid, and biotin. So 5 and B12. So 6 of the 7 B vitamins. You might as well need all of them. Calcium, magnesium, potassium, and chloride as minerals that you definitely need, with manganese playing a possible substitution for magnesium in one of the enzymes. So basically 6 of the 7 B vitamins, leaving out folate. And of course, every reaction is dependent on other ones behind it. So it's not to say that folate's not going to do anything to branched chain amino acids, but you could have if you have any block in ATP production, you're going to wind up having secondary effects in this pathway. But the nutrients in the first layer of the onion, the nutrients that you need are 6 of the 7 B vitamins: B1, B2, B3, B5, B7, and B12, lipoate, calcium, magnesium, potassium, and chloride. Those are the nutrients that you need to metabolize branched chain amino acids. Now, if you say you have a hereditary weakness in branched chain amino acid metabolism, well, which gene? Because there's this goes up to 17 because I removed 2 that weren't relevant to this discussion. So there's 15 relevant enzymes that have genetic disorders in them. The most common ones are deficiencies. So like the deficiency of the branched chain alpha keto acid dehydrogenase in step 1 affects all of them and is responsible for maple syrup urine disease and is often thiamine responsive. And then deficiency of isovaleric acidemia is not generally thought to be vitamin responsive, but it could be riboflavin responsive specifically. And this causes you to potentially smell like sweaty feet instead of maple syrup. Deficiency of beta-methylcrotonil-CoA carboxylase makes your urine smell like the urine of tomcats, and it can be biotin responsive. But the thing is, there's several principles here. So if you look at a textbook such as the one that I took this figure from, there is what I think is potentially misleading statements that some of these are nutrient responsive and some aren't. I went back and looked at the case reports, and I found that they were dismissing genetic deficiencies for being nutrient responsive on the basis in biotin of trying 4.5 to 20 milligrams of biotin. But there's a case report of not a deficiency here, but a deficiency in a different biotin responsive enzyme or biotin dependent enzyme, where it's considered non-biotin responsive and irrevocably lethal in infancy or early childhood. And this child was maintained relatively healthy and alive for many years after her death sentence on 1.2 grams of biotin per day. So I think that casts into question every case report that claims a genetic disease wasn't nutrient responsive, because they might have just 100-fold underdosed the vitamin. And so, generally these mutations they're not null, because if you have no enzyme, it's almost like completely irretrievably embryonically lethal. So you never have the passing on or even the chance to treat the infant in someone who has no enzyme whatsoever, unless there's another enzyme that offers compensation. So you never have a case where you could totally rule out any nutrient responsiveness. However, it may be the case that, for example, the branched chain alpha keto acid dehydrogenase, that enzyme has 3 components that all have, it's not that every part of the enzyme is dependent on all of these. It's that each component has its own active site that has specific nutrient dependency. So the specific mutation might increase your need for thiamine, but not the others. So you might have to megadose thiamine while you don't need to megadose riboflavin and niacin the same way, but you might get value out of them, right? Because if you have a genetic mutation that compromises the thiamine binding site of this enzyme complex, it's not specifically increasing your need for B2, but if you also have suboptimal B2 status, you're just going to make it all the worse, right? So if you have any hereditary weakness in any part of this pathway, you should be thinking about all of the cofactors, because if you have a deficiency or suboptimal status of any of them, you are going to make the situation worse. But that doesn't mean you need to megadose all of them. So you really need to look at, what's the specific dose I have? Is there any precedent that it's vitamin responsive? What are the doses used? And then you have to go by symptoms, and ideally the correlation of symptoms and biomarkers to titrate your dose of the nutrients there. And so you have to separate, what do you need to megadose and what do you need to just make sure you're not deficient or that you're optimal in. And that has to be hypothesis driven based on the mutation. And then it has to be data driven based on your symptomatic response and your biomarker response in well-designed self-experiments in order to optimize symptoms and biomarkers. Now, the last question is, does this influence your weight loss choice? Yes, it does, but perhaps not for the reason that you were asking. I can't tell why you were asking that. So if you were asking that because you thought your weight loss would be less effective because you can't break these proteins down, then not really. That's not really going to be a major impact. What is a major impact is that during weight loss, you are in a catabolic state. When you're in a catabolic state, you aggravate your deficiency in the pathway, and you have a greater risk of toxicity of the intermediates, right? So if you have isovalerial CoA accumulating because you can't break it down in the next step, you have 3 problems. So you have 4 problems. One is you can't break this down. The second problem is you have isovaleric acid accumulating, which can have toxic effects. Your third problem is you have CoA being sequestered, and you start leading to CoA starvation. And your fourth problem is that isovaleric CoA is a small enough CoA ester that can competitively inhibit acetyl-CoA dependent enzymes. One of those is the enzyme that activates the urea cycle, and so you can get secondary hyperammonemia as a result of this. So the reason that on a weight loss diet you need to be more careful about potentially limiting your BCAAs and megadosing your megadoses and optimizing your other nutrients in this pathway is that weight loss will stimulate the possibility of toxic responses to the pathway and symptomatic problems due to low-level poisoning. So, but you can have a SNP in this pathway and be asymptomatic. But there is some precedent for wanting to optimize the nutrients, even in those cases, due to the potential for subsymptomatic changes in brain health. So there's asymptomatic people that arguably should be treated with vitamins in order to not have a sort of like slow, lifelong degradation of myelin and stuff like that. So I think you need to look further into what the mutation is. You need to figure out this megadose versus optimize for each of the vitamins. And then you need to say, in weight loss, I need to double or triple my care for this pathway if I have evidence that I need to care about it at all, because I don't want weight loss to increase my catabolic state and therefore cause more of a problem here than I would have in a weight equal state, in an isocaloric state. All right, thank you, Melanie, for your question. Hope that helped.
This is a clip from a live Q&A session open to CMJ Masterpass members. In addition to this episode, you can access lots of other free samples from these sessions at the first link in the description. If you want to become a Masterpass member so that you can participate in the next live Q&A, or so that you can have access to the complete recording and transcript of each Q&A session, you can join at chrismasterjohnphd.com/masterpass. You can save 10% off the subscription price for as long as you remain a member by signing up at chrismasterjohnphd.substack.com/Q&A. That's Q&A spelled out as Qanda. These links are in the description.